Hello, everyone. My name is Jiayi Chen. Today, I'm going to present the video presentation for the Advanced Machine Learning course project. And this presentation is related to my final report of Advanced Machine Learning. So my project is an empirical verification of the low-intrinsic-rank hypothesis in LoRA. In this work, I investigate the theoretical foundation of parameter-efficient fine-tuning and test whether the assumption made in the original LoRA paper still hold up against modern, deeper architecture like Mistral 7 billion. Let's start with the background and motivation. So as we know, the full fine-tune FFT of large language model is computationally expensive and even computationally prohibitive due to a huge amount of memory bottlenecks. This leads to the adoption of parameter-efficient fine-tune, or PEFT, with LoRA being the standard. So the PEFT is a very famous Python package, and LoRA is one of the most popular method in this Python package. However, there's a gap in the literature. The original LoRA theory, the original LoRA paper were validated on older model like GPT-3 or RoBETA. My project asks a critical questions. Do these lower intrinsic rank assumptions hold for modern and deeper architecture? Specifically, I'm testing my questions and assumptions on Mistral 7 billion, a state-of-the-art open-weight model. To understand the experiment, we must look at the hypothesis. So this is the theoretical framework and diagram of LoRA. As you can see in figure 1 on the right, LoRA freezes the pre-trained weights, which is the blue box, and injects trainable rank decomposition matrix, which is the orange box. Mathematically, as shown in equation 1, the updated delta W is decomposition into matrix B and A. The core hypothesis proposed by Gupta and Seth Moyer in 2021 is that the adoption needed for a test lives in a low dimension subset. If that is true, we should be able to set the rank R to a very small number without losing performance. So with that being said, I'm going to walk you guys through the experimental setup. For my experimental setup, I use Mistral 7B version 0.1, which has 32 layers and with GQA attention architecture as the primary model. I also ran a control experiment using GPT-2 medium to replicate the original paper's finding. I used the Samsung dataset for abstract dialogue summarization. This is a complex generation test that serves a good stress test on my experiment. I fine-tuned the model across a geometric progression of ranks from 1 all the way to 64, while keeping the scaling factor alpha fixed at 16. Beyond just checking the experimental setup, I also want to walk you guys through with the subspace similarity analysis. So the objective is the quantified geometric alignment between low rank R equals to 8 and higher rank R equals to 64 updates. I use SVD, which is the singular value decomposition, to analyze the learned weight. Specifically, I calculate the normalized subspace similarity denoted by 5. This is the symbol 5. So as you can see, this matrix measures the overlap between two subspace. A value near 1 means the low rank update is perfectly aligned with the high rank update, which is the LoRA paper conclusion. However, a value near 0 means that they are orthogonal. Essentially, the model finds a completely different direction and solution. And this is the performance of my experiment 1. So let's look at the result. Experiment 1 tested performance saturation. If you look at figure 2 on the right, you can see the ROC score plotted against the rank. The results are striking. Performance saturated immediately. We achieved our peak ROC-L score of 35.47 at rank 1. Surprisingly, increasing the rank to 64 actually resulted in a slightly performance drop to 34.81. Well, likely due to overfitting. This confirms that functionally the test adaptation has an intrinsic rank of exactly 1. Before analyzing Mistral, I validated my SVD pipeline on a GPT-2 control run. So that is part of experiment 2. The heat map here shows the subspace similarity. Lighter color indicate higher similarity, and darker color indicate lower similarity. Consistent with the original LoRA paper, I observed a high similarity of approximately 56%. This confirms that in older models such as GPT-2 medium, low rank updates are heavily nested inside high rank update. So the control experiments consistent with the LoRA paper. However, when I applied this to Mistral 7B, the story changed. Overall, the similarity was much lower, averaging around 10%, 0.1. But the most interesting finding is the layer-wise divergence. The top row represents layer 0. As you can see, it's almost entirely 0 similarity as the color is towards 0. However, the bottom row represents layer 31st. And we gradually see some kind of similarity as the color-coded indicate. This alignment jumps significantly to around 20%. So this tells us that low-rank structure is not uniform. It emerged primarily in the deep layers. To summarize the geometric findings, the structure of the update depends heavily on depth. In shallow layer, such as layer 0 to layer 5, the optimization landscape is unstable. Different ranks find different solutions. However, in deep layers such as layer 21 to layer 31st, the model converges to a shared stable subspace. So this implies that core of the is actually residing in the deep semantic layer of the network. So with all the experiment conducted, here we come to a discussion. Why is Mistral so different from GPT-2? I concluded to 2 factors. The first factor is depth. Mistral is significantly deeper, 32 layers versus 24 layers. The adaptation signal appears to be distributed more thinly across the network. And the second aspect is from architecture-wise. Mistral uses GQA, grouped query attention mechanism, and GPT-2 doesn't. The low similarity suggests the modern deep model have a much larger solution space, allowing them to find degenerated but effective solutions that don't necessarily align geometrically across ranks. So to summarize, based on this, I propose the future works. We should investigate variable rank strategies. We should allocate higher parameter budgets to the stable deep layers according to our experiment too. And potentially we should prune or freeze the unstable shallow layers. So this kind of technique already has a published method called LoRA, so which is almost identically to my thoughts. With all that, we come to a conclusion of my presentation. In conclusion, we validated the functional hypothesis. You only need rank 1 to effectively adopt Mistral 7b. We refined the geometric hypothesis. The lower rank structure is not universal. It's strongly depth dependent. As a conclusion, the biggest takeaway is, while LoRA remains effective, understanding this non-uniformly is the key to adjust the next generation of efficient fine-tuning method. And that concludes my presentation. Thank you for your time.